Okay, thank you very much. Uh, well, this is one of those industry talks, just to be clear. Sorry. Um, a little bit my background for perspective. I spent nearly 4 decades at IBM, last 5 of which in IBM Quantum. About 2 years ago, I left, joined Inflection, formerly called Quanta, to look at, evidently there are other ways of doing quantum, neutral atom in particular, and some of the other things we do. Uh, but also, I want to ask your forgiveness, at least your understanding, that I am not a physicist. I'm only a mathematician. And also, I'm a software guy. I'm a hardware guy. So I am a little bit of an outsider on this, but I've nevertheless, in my professional role and some other things, been called on to explain quantum computing and to speak to people on the business side of quantum computing. Not being a physicist, I typically don't attend physics conferences on this topic, but I, like several other people in this room, attend many quantum conferences. Several of us within just the last 2.5 weeks were at Quantum Boston. The World Economic Forum in Geneva had a quantum conference. There's Inside Quantum Technology, Quantum Tech, the World Quantum Congress. So that is, there are many hundreds, if not thousands of people around the world talking at business-oriented quantum conferences, large and small. And so when you talk about business, these little concepts like return on investment, what am I actually doing? What does the thing do, right? Why should I invest in anything in particular? How's it going to improve my business? I'm not looking necessarily to experiment. I'm willing to do a little bit of an investment for research and things like this. So the questions and the perceptions are different. Okay. And what tends to come across in these conferences, if you listen to the talks, certainly not by every vendor, and by no means do I want to pick on anyone in this room, but because there are many quantum conferences and vendors, look, they've got to sell stuff, right? They need, so here's a word I never knew about in IBM, called non-dilutive funding, okay? Which means people don't just give you money, right? Venture funding, you actually have to sell things, right? And take that money and do things. And so the perception is that wherever we happen to be right now, whatever those businesses, those clients need, is just right around the corner. It's just next year. It's almost there. The next version, right? So jump in now. Don't be too late. Hire me as a consultant, right? Before it's too late. When in reality, somewhere out in the future, and here I'm not providing any numbers, just time is out there. It's where we actually really need to be to provide this economic value to real businesses and most businesses. One of the other problems with quantum is people love the world, right? I mean, I've been on the business side and with IBM, and let me tell you, there have been products that you just wish somebody would ask you about, right? Please buy this thing. And even I was bored with, to tell you the truth, the product I was trying to sell. But quantum people say, I want to know. There's excitement. It's a pull. Tell me more about quantum, right? Give me an excuse to buy one, right? And things like this. And so, the chasm that I was referring to was this idea of it's really not a straight line linear path from where we are today to where we need to go. There's a lot of work to be done. This fantastic work that's been done, much of which is described here over the last 2 days, but we are definitely in those early stages. And in many cases, as Chris pointed out, as Oliver pointed out, we've made major progress on the engineering side of this. That is taking prototypes, things that were in the labs, but actually starting to produce real products that people would want to use. And this chasm, though, you can't see it. Those are very sharp rocks, right? You never know what you're going to cross over there. And, the idea is, well, if we think about there as a bridge, we can cross from here to there. You have to be careful if you are on the sales side that you don't This bridge in particular, this is the Brooklyn Bridge. There was a famous con man in New York City in the 1800s who for only $50,000 you could buy the Brooklyn Bridge. And of course, it wasn't his to sell, but he did it many times, right? And he ended his life in prison. He sold many other public monuments as well. But the idea is that we will get there, and I'm very, very optimistic about quantum computing and things like this. But this sense of realism and escaping the hype. One example of hype, and it just never seems to escape, a vendor who I don't believe is represented here, I'm going to paraphrase, in the last week announced a 32-qubit quantum computer with not particularly great specs that is ready for the enterprise. Well, what's an enterprise and what does it mean ready, right? Well, they have a white paper. But I would argue that maybe that's not quite the case, right? Yet, if you are an enterprise person, right, big company, and you're thinking about this, so I would say they're probably going to have some issues with that particular phrase. And so one of the questions, and we all know that this is way too simple a question to ask, but it's the easy question to ask. And it's how people get wrapped around certain of these ideas and think they know more. And again, I'm thinking of clients, potential buyers, right? So how many qubits do I need to do useful work? Well, first of all, what do I mean by useful, right? In the context of my business. If I make dog food, please tell me how a quantum computer is going to make my life better, okay? However, if I'm in banking, it's a little bit easier argument. And this usefulness, is it scientifically useful? Is it demonstrating some principles, things we've seen here, which is great, is wonderful? Or this notion of commercial production application. Now, production application means you are a real company. You process transactions, and you buy and sell things. And you have all these IT systems and databases and all these sorts of things. I want to plug in a quantum computer and do something, right? I don't want to experiment. Really plug it in. And maybe it's going to be like an HPC, right? So it's not going to be an everyday type of thing, but it's going to be serious computation. So think of a hedge fund maybe as an easy way of doing this. And then we start confusing people with qubits, physical or logical qubits. And oh, by the way, what is a logical qubit? And I would tell you, if I went to any one of these other conferences, I would probably get about 30 definitions of what a logical qubit is. Some of which are probably close to being right. And of course, they hear about error correction. They hear about fault tolerance. And sometimes people use this as kicking things down the road. That is, from a marketing perspective, well, my computer is small now, but just wait for error correction, right? Now, error correction, of course, is critically important. We need to do the key research. But here I'm talking about the perception of what is being sold in the industry. And we all think this. And then we get into questions about physically connected. Is it 4 to 1? Is it 2 plus 3 to 1? Is it all to all? Is it whatever? And actually, do I really care? But it's just a fascinating sort of topic. But really the question is, well, I need these, and when can I have them? And by the way, what sort of response are you giving? Are you giving me a physics answer, an engineering, or a marketing responses? And most of the problem, I will tend to put in marketing responses, but I have heard very technical people say absolutely ridiculous things for the sake of commerce. It happens, right? So, let's get into this, and frankly, I didn't know what numbers to put here. This seems like fairly consistent with Carl's lower bounds from yesterday of just starting to do something interesting. You can argue about these numbers forever. How good are your qubits and things like this? The main point being is that these numbers are much larger than what we've got today, right? That's the main point. And oh, by the way, and Chris, you pointed out, you tend to do a whole lot of gates on individual qubits, so you're probably going to have interesting depths. Look at the quantum Fourier transform. Start counting gates and things like this, and how deep those circuits get just on very few qubits. So you need to do a lot of operations on a lot of qubits. And so it's a trade-off. If you give me a lot of qubits, but I can't do much with them, well, thanks, right? If you give me a few qubits, but I can do a lot with them, well, I can't deal with big problems. So all of these things are these different trade-offs. Now, I was scooped by Irfan this morning on the third quantum revolution. This is my mistake of giving my slides in too early. But the idea is fourth. Oh, is it fourth? Okay. I'll do the fourth. Okay. But the idea is wherever we are now, the next one will be the age of the really big quantum computers that we will get to eventually. And what do we have to get there? Now, this is the second analogy. Since I put Chasm in the title, I felt I had to go there. But this is sometimes, again, what users actually may know they need, particularly if they look at the capacity, the types of problems. But what we sometimes sell them in reality is one of these things. They're both modes of transportation. And, you know, we provide them with slightly larger wheels and it's maybe gold-plated and things like this. And this could sound terribly pessimistic, except at least from the perspective of the United States, you know, the Wright brothers, the first airplane, well, what did they do for a living? Before that, they had a bicycle shop, right? So keep going, is the point. But this is the distinction, remember. And oh, by the way, if you're talking to the government, they really are thinking about something like that on the top, right? And increasingly funding for all things quantum are coming from governments, particularly ministries or departments of defense. Now, there are a lot of considerations that we have to bring in, and these have all been talked about in some way, mostly the ones on the right-hand side where we talk about coherence time. Well, that has to be held together with gate speed. Long coherence times are great, but if you have really slow gates, well, you may lose. Circuit depth, right? Can you do multiple things at the same time and not chip your coherence time? More and more, though, people are actually looking at the left-hand side when they bring this. So what is the overall execution, right? And I think, you know, there have been some, Microsoft did some things. IBM introduced CLOPS and the new CLOPS H benchmarks. But these other two areas of cost and energy are very critical, right? So cost, okay, well, that's a great big problem, but how much is it fundamentally going to cost me to run it? And do I care that much? Because, you know, I have a number of different things I can spend money on, and maybe that's not where I'm going. So as we consider different modalities, right, will one be fundamentally slower, faster, more or less expensive than the other? And when you talk to groups like the World Economic Forum that take obviously a very global view and having quantum technologies in lots of countries around the world, they, like the UN, are very serious about sustainability and energy use. And most providers will have to provide some real numbers that relate what they are doing to how much energy they're actually going to compute. And that may come down to saying, you know, I'm willing to do this little slower thing if it uses less energy, and so forth. So this is why it's not necessarily cut and dried, what will win, what won't. Now, so Chris, you raised the point of modularity. I call these quantum cores, just for comparison to the classical. I had one of the original IBM PCs. It was barely a computer, you know, back in around 83, 82, 83. And really, I didn't even remember until I looked this up, that it wasn't until 2005 until we went to dual core. Ooh, right. 2 processors on the same chip. That was pretty exciting. And now, right, if you look at your Apple iPhone, the numbers are really pretty impressive. This is only a 14, not a 15. So 6 processing cores, 5 GPU cores, and 16-core neural engine. Well, quantum computers are going to have to do this. Supercomputers can have thousands of these things. And, well, you know, on one hand, you can think homogeneously, and here these may be superconducting chips. They could be neutral atom arrays. They could be atom traps. They could be whatever. However you package groups of qubits, there's some maximum number you can put in them, and that's your size of your core, all right? But you're going to have to connect these. And these are quantum interconnects. If you're lucky, you get some of these things for free. If you're photonic, maybe if you're microwave, it's easier, but a lot of us are going to have to do photonic interconnections, and with the noise that might be. We simply have to do to scale. And so it behooves us to have larger cores so we don't do it. Which raises another question, which is this notion of transduction, of going, however, I have my qubit states inside my core, how do I move it to optical to move it somewhere else? Now, the point I really want to make with this, and this is the basis of talking between computers, between cores, between other computers, and lots of things, is I personally do not think the industry is investing enough in transduction. That is, we're worrying about getting larger and larger little cores. If certain companies would almost just stop and say, I am going to be fixed at X cores for the next 2 years, but I'm going to nail this problem, right? And then start increasing the core and increasing the core. I think an awful lot of them are focusing on having these little cores. They may do it because of the investment and things like that. But I think a lot of them will run into serious problems, that eventually the world will be littered with very small cores of interesting technologies that just simply can't go for this reason. And this is the basis of quantum networking. And quantum networking goes all the way down to the core. And that's something that's very different from classical networking here. Machine learning has been mentioned, quantum machine learning. There's a massive problem called the input problem. You can't move a lot of classical data into a quantum computer. It just takes a long time. You've used up your coherence time. Loading some of the data, you can't do anything with it. But if you have data that's already represented in a quantum form, such as maybe coming out of a quantum sensor or from the middle of a computation, then maybe you can do some interesting machine learning. And that's where I think in particular, those interesting applications will be. Software is going to be critical. And I want to put a vote for a future workshop on quantum software and all it means, by the way, here. We've done a lot with compiler technology. We're at the early stages of classical quantum technology. We're at the early stages of quantum compiler technology and optimization. There are general transformations. They're hardware specific. These cores will complicate things quite a bit. There will be a lot of computer science PhDs. There will be other conferences where they're talking about optimizations. In fact, there are already. And I took a lot of time trying to get the slopes right, and I couldn't. I gave up. But all I'm really saying is that, you know, over time with computing technologies, coders tend to have a lot more coders than engineers on the hardware side, right? That will happen at some point. It's a little ways down the line. So this is going to be a very, very rich area for what really makes quantum a reality and useful with these boards. So the very last slide here, workforce development is a very popular topic. Politicians love it. They want more jobs. They want more educated students in their areas. Look, education is a good thing. I mean, for all the reasons we want, but we don't necessarily need thousands more physics PhDs. Eventually, we're going to need people who know how to manufacture these things, right? Quantum today is very much a handmade type of industry. So we're going to need a lot of different people. But the quantum workforce, even with the new programs that are being started, such as at Princeton, is increasing extremely slowly, very slowly. Yet if you look at the number of quantum companies, that's increasing pretty large. So you got a problem where you have a slowly increasing resource on one hand and all these people, you know, want to go to lots of other places. But to become successful and move to the next stage, you have to have these established companies have more of the experts. They need to grow. So I think from an investment perspective, if I had already made investments in companies, I would focus less on new companies and I would do more to vertically integrate the company I have with the experts, right? So it's a question of workforce balance and where we put them. We maybe have enough quantum computing startups, at least for a little while. You know, let's try to build big systems that people will really use. So with that, thank you.